Okay, so it's clearly time for examples. Well, our first example should be the real numbers themselves. So you could take the set x equal to the set of real numbers, and the distance of two real numbers x and y is what you experience as the distance between 2 points x and y. It's just the length of that segment that connects the points x and y. How do you compute it? Well, you could say it's x minus y, but sometimes, like in this case, you would get a negative number, so you better take the absolute value here, then you don't have to care which one's left, which one is right. Okay, so this should definitely be a metric, a distance function, and it is. Next example. Okay, let's better check this. Okay, let's I mean, this is our first example. We should check what we say, what we claim. So the first property, remember which one that is? It says the distance is 0 if and only if the elements are the same. So when do we get 0 for dxy, which is x minus y? Well, we know the modulus of real number is 0 if and only if that real number is 0, and that of course means x is y, and that's how you check property 1. Property 2, you have to check whether the distance of x comma y and y comma x are the same. So the distance of x comma y is modulus of x minus y. We want to arrive at d of y comma x. What is that? Well, it's the modulus of y minus x. How do we bridge the gap? Or we could say this is the modulus of minus 1 times y minus x, right? And therefore it's the same as just the modulus of y minus x. Okay, so that's how you see this. And then the third property is the triangle inequality. So you want to check that d of x comma y plus d of y comma z is more or is greater than or equal to the distance of x comma z. Translating that for our example, it would mean that modulus of x minus y plus the modulus of y minus z is greater than or equal to the modulus of x minus z. How do you see that? Well, you make life a bit easier, I think, if you call this one here A, maybe, and this one you call B, then what do you think is this? Well, it's easy to see that this is just A plus B, right? Because if you add A and B, you get x minus z, you get x minus y plus y, which cancels, minus z. Okay, and now I think you've seen that before. This is the triangle inequality, as you call it, for real numbers. So we can also tick that box here. Okay, so this is indeed a metric space. Let's look at something more interesting. So the next example could be R2. So it's getting a bit more, a bit higher dimensional. Or let's get crazy. Let's just get R to the power n. How could we choose the distance of 2 points x and y here? Well, if x is the vector x1 to xn and y is the vector y1 to yn, then you could take the length of the line segment connecting these two. You know what I mean? You look at the difference vector at x minus y, which is then x1 minus y1 up to xn minus yn, and you ask for the length of that. So you would take the square root of x1 minus y1 squared plus and so on xn minus yn squared, right? So in the end what you get is just the length of the vector x minus y, which connects the points x and y, right? Should we try to check whether or not this is a metric? Distance function? Well, to start with, we would have to check whether when is the result equal to 0. Okay, so when do we get 0 here? Well, the root is 0 if and only if the thing underneath the root is 0. Well, that is just a sum of squares. So here's a square, and then here's a square, and in between there are some more squares. Each one of these squares is, of course, greater than or equal to 0, and the only way to add them all up to equal 0 is they are all equal to 0. Because as soon as one of them is positive, you cannot compensate that down to 0, because you cannot have negative squares here. We are in the real numbers, right? Real numbers. So this is indeed the case if and only if x1 minus y1 is 0 and ... and xn minus yn is 0, or in other words, the vectors are the same, right? X and y are the same in the first component, in the second component, and so on, in all components. So again, we have checked property 1. Checking property 2 is also not difficult. So you just look at d of x comma y, and this would be like we saw before. What is different if you look at d of y comma x? Well, for d of y comma x, you would just exchange these here, which makes the term in the bracket just a negative of what it was before, but then you take squares, which just ignores the negative, and you add up to the very same expression. Okay, so okay, so indeed they turn out to be just the same. Right. Checking number 3 is, to be honest, not much fun. 3 is also correct. Also correct, but not much fun. We will discuss that at some later point. Not this lecture, I guess next week. So let's postpone this a little bit. Okay, so the 2 examples so far are actually are not even 2 examples, because example A is a baby case of example 2. So far we've seen only 1 example really, which is r to the n. And it's not a big surprise that r to the n with the usual Euclidean distance is a metric space. So the Euclidean distance is a distance. So let's look at some examples that are maybe not so standard or not so unsurprising. Okay, how about that? So we take the set x to be the set 0 and 1 to the power of n. So what is that? Well, you take n elements, each of which is either 0 or 1, and write them one after the other. So e.g. 0, 1, 1, 0 is an element of 0, 1, 4, okay, because it has 4 digits. Now you will say, now this is not correct. It's only correct if I take bracket, comma, 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 bracket. And of course you're right, but let's not be too picky here, okay? Let's interpret this vector of 4 elements with just a little string, just a simple sequence without commas and brackets, consisting of zeros and 1. You could say a binary number with 4 digits, okay, or in general a binary number with n digits. Now you want to compare such binaries and you want to measure how far is one away from the other. For example, if you want to detect errors in your transmitted code or something. So what's a good idea for a distance? So you could say the distance of 2 such n-bit binaries is the number of bits where x and y differ from each other. So e.g. the distance of 0, 1, 1, 0 and 0, 1, 0, 0 is 1 because they only differ in one position, okay? Maybe you've seen that before. It's the so-called Hamming distance. So this is the so-called Hamming distance. And the word already suggests that it is a distance function. It is a metric in the sense of our definition, but still we don't trust in words, we need proofs. So there we go. Property 1. When do we get 0? We get 0 equal to dx comma y. Whenever the number of bits where x and y are different is 0, that means, okay, they are equal everywhere, okay? They are nowhere different. X and y are nowhere different, which must mean they are the same. Okay, that was easy. Number 2, okay, comparing x and y and comparing y and x obviously leads to the same result because the word differ is symmetric, right? So for the word differ, it doesn't matter whether you compare x to y or y to x. It gives you the same answer. So also that is easy. And now number 3, the triangle inequality. So we would have to check that d of x comma y plus d of y comma z is greater than or equal to d of x comma z. Is that easy to see? I am not sure. Let's do it as a extra problem. It's not a 6, it's a Q. So this is one of our extra problems that we should discuss in the Zoom problem session this afternoon. Let's look at one more example. Example D. The set X, this time it doesn't matter at all as long as it's not the empty set like we want in the definition. And we say that the distance of two elements x and y is 0 if they are the same and 1 if they are not the same. Doesn't that look crazy? So we don't really worry about distances at all. We just say the only thing we care about is, are they the same, yes or no, hit or miss. Okay, is that a distance in the sense of our definition? Is that a metric? Let's check. Property 1, when do we get 0? Well, we get 0 if and only if they are equal, right? Because here it is. You get 0 if they are equal, and you get not 0 if they are not equal. That's all you have to do. Property 1, check. Property 2. Can I exchange x and y here? Yes, of course. Why? Well, because I can exchange them here and here without making any difference. So also that gets a check. 1, 2, 3. 1, 2, 3. Okay. Property 3. The triangle inequality. Okay, I could post this as another extra problem, but let's be serious. We should do something here also. So d of x comma y plus d of y comma z. Is this really always greater than or equal to d of x comma z, no matter what x, y, and z is? Okay, you could look into a whole lot of cases. I mean, case 1, x equals y but not equals z. Case 2, y equals z but not equal to x. Case 3, x is z but not equal y. Case 4, they are all different from each other. Okay, you could go through all cases, see what happens, and then finish up. I don't like these many cases because I'm never quite sure whether I'm catching all. Let's try to be clever here. Okay. Suppose not. Suppose not. Suppose it's not the case. Well, then we would have not greater than or equal means probably less than, right? The only numbers we get here for distances are zeros and ones. How can you get less than by only using zeros and ones? The only way to get that would be to have a 0 here, a 0 here, and a 1 here, right? Because, I mean, how do you fill these 3 slots with zeros and ones in order to make this true? That's the only possibility. 0 plus 0 is less than 1. But if you did that, then that would mean x equals y, because distance of x comma y is 0. That would mean y equals z, because the distance of y and z is 0. And that would mean x is not z, because the distance of x and z is not 0, it's 1. You see the problem? I mean, if x is y and y is z, then you get that x is z, which of course totally contradicts this thing here. So this is the contradiction. This means our assumption that it's not true is wrong. So yes, it holds. This particular metric, which you can use on any space you want, as long as it's not the empty set, has a name. It's called the discrete metric. Discrete metric. Okay, discrete because you do not get a whole lot of different answers for D. You only get 0 and 1. There's only 2 different answers, and I guess that's why it's called discrete. Yeah. We might come back to that. Let me give you one more example. So let's get back to the good old R2, but let's try and equip R2 with a funny distance, and let's check whether or not it's a distance function. So d of x to y, which are now points in 2D, okay, shall be the usual norm of the vector x minus y if x, y, and the origin are on the same straight line, right? Okay, so you have a situation like this. So here's the origin, maybe here's your point x, and if y is maybe here, so that you could draw a line through the origin and x that would also contain y, then you're in case 1. So in that case, you would say that the distance of x and y is just the norm, the length of the vector x minus y. So you would just get the usual Euclidean distance of these 2 points. However, if that's not the case, then we define it as norm of x plus norm of y. Otherwise, so this is okay. So this is case 1. So here's case 2. So suppose x is here and y is not on that line; it's somewhere else. Okay. Then what did we see? Well, we get that the distance from x to y is the length of the vector x plus the length of the vector y. So it's the sum of these 2 black lines rather than just the length of the direct connection from x to y. Indeed, this turns out to be a metric also, and it's called the French railroad metric. Now you can guess why this is so. Well, maybe let me tell it to you. Apparently in France, if you want to travel by train from town X to town Y, you almost always have to travel via Paris, which is the origin of France. So you travel from X to Paris and then from Paris to Y, which gives you the second case. Why did I say almost always? Well, because of course, if X is on the way from Y to Paris, then, well, you wouldn't be stupid. Then you would, of course, not go all the way to Paris. You would rather stop your journey to Paris already when you arrive at X. That is case 1, but it's, of course, very unlikely. We didn't prove that this is a metric. You can do it if you want. If you want to practice these things, then please feel free to check properties 1, 2, 3 here also. Okay, so we have seen that a whole lot more or less exotic settings fit into this framework of metric spaces. And we can still give some sense to the word distance that is at least subject to our properties 1, 2, and 3.